Hi everyone, I'm Josh. Here's my project on developing a gaze-based large language model-driven keyboard. So to kind of motivate this project, I'd like to go over some existing solutions. Got a nice little GIF for those of you who don't have good attention span. So on the left you see Dasher. So essentially how this system works is, you look to the right-hand side of the screen, and as you look there, characters start increasing in size, and as they reach that kind of middle line, they get selected. So how it kind of determines what characters appear on the right-hand side is quite ingenious. It uses a language model to kind of probabilistically determine what's the most likely character to come next. And then you've got kind of a standard design, a tree-based solution, where each button on the keyboard contains, it's like a sub-menu. It contains sub-menu, and it has all the characters that will be contained on the keyboard when you press into that. So there are some problems with these kind of designs. So with Dasher, as many of you can probably kind of see, it's a bit disorientating, a bit difficult to kind of keep track of where everything is. And with a tree-based solution, you end up having to press a lot more buttons than there are characters in the word you're trying to type. This is because in the first press, you have to go into the sub-menu. The second press, you're depressing a character. And in the third press, if there is a back button on the keyboard, to get back to that original menu, you have to press that back button. So you can see that'll be very frustrating. Naturally, right, as humans, we don't use our eyes to point. The idea of gazing is that it's quite an unconscious activity. So how do we kind of mitigate some of the problems associated with current designs? So something that I kind of played around with was, what if we don't need to use every single character on the keyboard, right? What if we could use a completely reduced character set so we could fit, I don't know, maybe 8, 9, 10 characters on the keyboard simultaneously so people wouldn't have to navigate through these menus. So let's go through some definitions, right? Let's just say K is this keyboard with a reduced character set. And let's introduce this concept of a wildcard. And a wildcard is going to represent every character in the alphabet, but not in K. And that's quite an important definition, that one. Just keep that in mind. So how would typing with this keyboard look like, right? Let's assume we want to type the sentence, the cat walked, right? We'd start off by typing, so T's on our keyboard, we can see there's no H and there is an E. So we type it T percentage sign E, percentage being that wildcard, right? So just a question to the audience, right? If I were to give you this spelt sentence, and I would say, what do you think that word could be? Can anyone kind of think about, if they didn't have the original sentence, what T percentage sign E could be? Anyone? Toe is a good one? Tie is a good one? Right. Now, remember that definition of a wildcard, right? It's only the characters that are not on the keyboard. So we can kind of, so it's like you said, who said tie? Was it you, Ollie? Yeah, perfect, right? Now, the problem with this, toe is also a valid solution, but the definition of wildcard allows us to prune things, right? Tie is not actually a valid match because I is on our keyboard, which means we kind of make this assumption, which is a very large assumption and kind of a double-edged sword, that people are going to be typing with 100% accuracy, right? People won't, but you kind of, to exploit as much performance out, to extract as much performance as you can out of the system, you kind of need to make that assumption. Right, what about a different case where you have multiple valid word returns? So you're typing the cat, right? C percentage sign T, you have things like cut, cot, and cat, right? These are all valid matches. Now, this creates a bit of a problem, right? Because now there's a lot of ambiguity in what the word could be. The cot could work, the cat could walk, both of those work perfectly fine. How can you discern which one is correct and which one isn't? Well, this is where a large language model comes into play, and this is where we use ChatGPT, right? So by using the entire context of the sentence and passing it over to a large language model, you can kind of get it to fill in the wildcard characters using the context of the entire sentence. Now, I know as computer scientists we don't like talking about project management, but I think it's important because in this case, we want to make this as accessible as people as possible, making it as cheap as possible, making it so that anyone can use it regardless of, financial, whatever, status, whatever. So imagine a situation, this is for 10 million tokens, I've got the pricings up here. So you can see for GPT 3.5 Turbo, for 10 million tokens, it costs 50 cents, or $1.5 for output tokens. And for GPT-4, for input tokens, it's $10 for 10 million, and $30 for output for 10 million. So what is a token, right? This sounds like quite an abstract word. So let's look at this idea of tokenization. So tokens are common character sequences in text sets. Models use them for processing, and OpenAI also bases pricing on this information. So they're just kind of the way we break, the model breaks sentences into processable chunks, right? So if we think about that earlier thing about 10 million tokens, right, that means for 25 tokens, which is the average kind of sentence, if we assume that, we can process 400,000 sentences, right, for $10, $30, whatever. This is, it's an economies of scale issue, and it shouldn't matter which one we use. It won't be that expensive for an individual user either way. So we can use either one. So this is where, if you are overly concerned about my budget, right, you can donate in the name of academic grant. Now, I did try this in my dissertation presentation, deadpan. Don't make jokes, guys. It's not going to work. Right, so how does this algorithm kind of work? Right, so the initial idea that I explored was this single try approach, where you pass it to ChatGPT, and it tries to instantly guess all the wildcards all at once. There is kind of a problem with that, because sometimes what happens is GPT kind of adds additional words into the sentence. Sometimes it guesses words incorrectly. You can see, for example, jumped kind of fits that pattern well, right? So, we got to kind of come up with a way around this. I think it's also important to note that accuracy I'm going to define as the number of words that I guess correctly, and they also have to be guessed in the correct position. So you can see that cat is highlighted in a kind of a yellowy color because even though it matches that pattern of C percentage sign T, it's not in the correct position. So how can we rectify this issue that the single try approach has? Well, this is where we kind of introduce an iterative approach, right? So what happens here is we take the output of GPT, we do some post-processing in it, and we feed it back into the model. So what does that post-processing look like, right? So it takes the form of a two-pass zip. So in the first zip, we have a forward zip, right? So it kind of matches the first item of each tuple is the first word from or is a spelt word, so a word spelt with a keyboard. And the second item of each tuple is a word returned by GPT. So we'll have no wildcards. We do it in reverse as well, so we have a reverse pass, right? And what's the idea of this? The idea is by doing this, we can kind of identify all of the correctly guessed words, or some of the correctly guessed words within the sentence, and if it is a match for the wildcard, so for example, jumped, well, actually that's not a good example, the is a match for T percentage sign E, we can include it into the sentence and then repass it to GPT with some additional context, and hopefully the next guess will be slightly better. Now, some of you may have noticed jumped isn't actually correct. Again, using that assumption about wildcards, we can prove it because J is on our keyboard. So we make that assumption that the user would have used J if it was there. This is obviously a limitation, and if any of you are looking to kind of explore this further, please try and fix this. Okay, so yeah, again, words must be spelled with 100% accuracy. So we put it all back into the original sentence, and then we can pass that to GPT, and hopefully we'll get the correct answer after a few more iterations, perhaps. But to effectively do this, we have to go through a process of prompt engineering, which is a fancy title. A lot of people have been giving themselves prompt engineers and whatnot. In my case, this was quite an iterative process. If you kind of think about the idea of what I'm doing, the percentage signs, the wildcards, are kind of like unguessed characters in Hangman, and the guessed characters or the letters you have on your keyboard, it's very similar to Hangman. So this was a system prompt, or the context that I passed to GPT to be able to better solve the problem at hand. I tell it what characters it has on the keyboard. I tell it not to reuse any of them. It does sometimes, but of course that iterative approach helps to mitigate that. Right? So then I pass it this blueprint. Now, this blueprint's quite interesting. It's a strategy called one-shot prompting. Essentially, you give GPT an example conversation. The user is you and the assistant is GPT. So in this case, you're saying, okay, this is the current sentence, which is some sample that I give it. I ask it, what do you think it says? And then I kind of simulate its response. And in that way, what I can do is I can quite accurately predict what GPT is going to respond with. So for example, that colon and that speech mark I can search for in its reply, so I can extract only the data I need. It also helps it answer with a bit better accuracy as well. So that's my prompt. But obviously, when you're using a language model of any kind, there are going to be some ethical implications of this. Right, it's been noted that large language models tend to have quite significant political bias towards the left of the spectrum. There's a lot of restriction of speech. You can't swear. You might not be able to use the slang that you want. I guess that follows quite nicely into the fact that it can be quite exclusionary to certain linguistic groups. If you're speaking in a specific way, perhaps even if you're speaking a different language, it's not going to be as easy to detect as if you're kind of speaking in English and standard way of speaking. I guess this all comes down to now, which letters are actually necessary, right? We would like to have the standard QWERTY keyboard, all 26 letters, but we can't do that. So this is where we do some simulated annealing. So what is simulated annealing? Anyone do AI in here? Yeah, probably some of you. Yeah, for the rest of you, tough luck. So in essence, though, we're trying to minimize some scoring function. And in this case, my scoring function is going to be the number of matches that are returned for a configuration of characters. So in this case, you can see for the word cat or C%IT, there are 3 words returned. So naturally, the graph of this kind of looks, well, yeah, it looks like this. So for a 26-letter keyboard, it's kind of as we expect. You spell every word without wildcards. There's no ambiguity. So a number of times, only 1 match is returned is every single time. And as you decrease the number of characters, the number of times a single match is returned is considerably reduced. But the total number of words returned also exponentially increases. So to kind of think about which character set I wanted to choose, we first had to go through a bit of a design iteration. It was quite jumping back and forth. So initially what I thought was, okay, let's have every button the same size. Let's say that we can fit, 12 buttons. Is that 12 buttons? I hope so, 4 by 3, yeah, 12. 12 buttons on the grid, all equally sized, all equally spaced. This was an intuitive idea, but it kind of forgot to think about one important concept, which is Fitts law. If any of you know what Fitts law is, it's a function which basically says that a button's difficulty to press is a function of its distance and the size. And what that means is, a side effect of that, is that buttons on the edges are actually easier to press. Think about using your mouse to try and press a button on the edge. Your mouse is bounded by the screen, right? So you can't really go further out. But the buttons in the middle are quite hard to press because you have to be very precise when moving your mouse. Right, so what can we do with this idea? Because buttons on the edges of the screen kind of extend infinitely along the edge they border. Well, what we can do is we can change the size of the buttons. We know that buttons on the edges are easier to press, so we can reduce their size. Buttons in the middle are harder, so we make them bigger. But you can see here that between the previous design iteration and this one, that bottom row hasn't changed too much. Why? Well, let's see what we could do. Like, we could probably fit another character into it if we followed the principles of that first row that we tried doing. But this looks a bit ugly, doesn't it? And in terms of symmetry, we have some issues. Right, this is a product that people are going to be using a lot, and so design plays a large impact on the usability of the product. So these are things that we have to consider, and symmetry is a big part of design. And so, we'll explore the advantages and disadvantages in a second. Right, so from those designs, to fit all these characters in a single menu, we saw the 8, 9, and 10 character variants were kind of where we were looking at. So we kind of narrowed down our search a little bit. So going through the GPT algorithm I discussed earlier, remember that accuracy we define as the number of words that have been correctly identified in the correct position. I notice as well that I'm saying we a lot, that's because I'm a bit of a one-man army. So you can see for the GPT 3.5 models, scores are lower, GPT 4.5 is higher intuitively, right? But look at that 8-character keyboard, right? We have such a large spread of values. So that's when I decided that this wouldn't be acceptable, and so kind of cut that out. You can see for 9 and 10 letter keyboards are the only one that remains. It's important that every 0.01 point of accuracy is really important, right? That is an additional word that is guessed correctly. Obviously, you're not going to be able to get 100% accuracy. That's not going to happen. When you're introducing uncertainty, there are going to be words that are guessed incorrectly. So let's get rid of 3.5 because we saw that 4 is cheap enough that we can use it. And that, the difference between 9 and 10 is very minimal, and the design benefits from having a 9-letter keyboard significantly outweigh having a 10-letter keyboard. So let's chop off the 10-letter keyboard. So what the design actually ended up coming to was this relations board, a bit of a cringy name, but it's named as such so to represent all the characters that are on the keyboard, R-E-L-A-T-I-O-N-S. Some of the interesting features, obviously, you've got these resized buttons, so buttons on the edges are a little bit smaller than buttons in the middle. You've got this idea that when you're looking at a character, it highlights in green. And you've got those multiple delete buttons for a bit of redundancy, depending on where you are on the keyboard. You might want to use one or the other. So how did I implement the eye tracking? This is where I use WebGazer.js. It's an easy-to-implement eye tracking software. You can use it through an API. Very, very simple. I didn't code anything. It's just a pre-implemented solution. It took a lot of time out of my project, so I was able to focus on the more interesting stuff. But there is a problem when you're using pre-implemented solutions, and in my case, this was gaze prediction accuracy. This plagued my project for a really long time. It's very difficult using just a webcam to precisely predict where you are looking on the screen, right? That's why I have things like Tobii eye tracking systems, which are a lot more expensive and use infrared to detect the position of your eyes. So I had to come up with a solution around this, and this took form of something called a cursor, right? So essentially, just to explain this, you've got my keyboard, you've got that gray triangle looking thing, which is a cursor, and then you've got the predicted gaze point, where the system thinks you're looking, and you've got a blue point where you are looking, right? You'll see that blue point appear in a second. So the intuition behind this cursor is it kind of lags behind where you're looking, right? Now you're looking to the bottom left, it goes to the bottom left, you're looking at the bottom right, it goes to the bottom right. It's kind of lagging behind you. Now, why this is important is because gaze prediction accuracy isn't going to stay solid. It's not going to stay at 100%. You're going to lose calibration as time goes along, your head's going to move, maybe you need to scratch, I don't know, something's going to happen, and you're going to lose accuracy. So the power of the cursor really comes into play here, right? Essentially, you can think about it like this, right? If I was looking at the ceiling, the gaze predictor would predict at the top of the screen. So you can direct your gaze above the dead zone that's formed, and then you can kind of have that momentary position point where you can depress that button. So it helps kind of navigate around dead zones. To see this in practice, I have a little demonstration for you guys to watch on how this works. So essentially, you'll go through a bit of a calibration process. I won't force you to watch all of this, but that red dot represents your gaze point, and the user's kind of looking at the square boxes as they go around. I'll skip ahead a bit. No one wants to watch 2 minutes of calibration. Right, so we get into our keyboard, and you can see that there's a red dot on the screen which represents your gaze point, and you've got that white cursor. So that cursor is following the eyes. You can see T percent sign E. Now you see here single word replacement occurred. There was only one match that matched the pattern defined by T percent sign E. So we could automatically replace it, right? So they're typing the classic phrase, the quick brown fox jumped over the lazy dog. So we'll give them a second to do this, right? You get the process. You can see that there are some arrows in the bottom right. That's because when multiple matches are returned, I kind of wanted to give the user the ability to cycle through them, a bit of flexibility of use there. In the final iteration of my design, there were some problems with that, but if you'd like to kind of figure out more about this, you can talk to me after. Okay, so as they go through the process, right, they go to the end. Let's get them here. Okay, they typed dog, space, full stop. Right, it goes to GPT, does a bit of processing. There were a lot of wildcards in the sentence, right? And there we go. It's replaced every single wildcard pretty accurately. Sorry, I don't know if you can see that quick brown fox jumped over the lazy dog. So it works really well, which I was quite proud about. Yeah, so that's my project. Thank you all for listening.